Okay, so now we are, so let's go back to where we stopped. So now we will talk about the indicators. And you're already familiar with the acid-base indicators. We did this in Chem 11. We use phenolphthalein, if you remember. And the acid-base indicators, there are the solutions themselves are usually weak organic acid or bases. Um, and what is important here, they have a different colors. Ionized and unionized form of those indicators, they have different colors. And that is important because indicators will tell us that we are near the equivalence point, and that's where we call it end of titration. We stop titrating when we see the color changes. So let's say we have an indicator. So let's say the indicator is a weak acid, like it's a general formula for the acidic indicator HIN, and that will have a conjugate base in the water. And they have to have a different colors. So they have to have one color in when they're in acidic form, a different color in a basic form. And if it's an acidic solution, the color comes from HIN. If the indicator is in its basic form, it will come from IN minus. So as I was talking, endpoint of a titration is a point when the color of the indicator changes, and there is a range of pH over which the color can change. It's not like a specific point of the pH, so it's like a range. And if we're doing some acid-base titration, and if we know at what point, at what range the pH, the equivalence point happens, then we can actually select an indicator where they change the color um, happens over the pH range that is matches the that stiffest part of a titration or the pH of a titration or the pH of the at the equivalence point. So if we know that, if we know the pH, what the pH of the equivalence point would be, we can find the appropriate indicator. So, so if I have, let's say, hydrochloric acid and the acetic acid, let's say both of them titrated with the sodium hydroxide. So as you can see, this one should, of course, be hydrochloric acid because it's a strong acid and the pH will be very low. And so we know that at the equivalence point, strong acid, strong base, the pH at the equivalence point is 7, right? But if we have acetic acid and the acetic acid is a weak acid and also being titrating with a strong base, we know because it's a acetic acid is a weak acid, at the equivalence point, it will have a strong conjugate base. That conjugate base will make a solution basic. And so that's where in that range, our equivalence points will happen. That means we have to choose a indicator that will change the color uh, around that range. So, but the phenolphthalein, take a look at that, changes the color when it's 8.3. The range is pH is 8.3 till 10. You see the methyl red, 4.2, 6.3. So really what is more suitable here for those two titrations are the phenolphthalein. Um, a lot of time we just use phenolphthalein, but in some cases we can use methyl red. So, well, as you can see, phenolphthalein and methyl red are the indicators that we can use for the strong acid, titrated with the strong base, because both endpoints coincide with the steepest part of that titration curve. But the methyl red is not suitable when you have acidic acid with a sodium hydroxide. So you see, this one will change its color much faster when the equivalence point will happen. So in that case, we need to use a phenolphthalein. But once again, as I was saying, a lot of time we just use phenolphthalein. But methyl red will be okay for the strong acid and a strong base, but not for the weak acid with a strong base. So this is giving to us some common acid-base indicators, the names of those: thymol blue, bromophenol blue, methyl orange, methyl red, so on. And they're giving us the color, what color they have in acidic solution and in a basic solution. And they're giving us the pH range when they change their color, when they change their color. So it means that prior to 1.2, that will be a red color. And the change happens between 1.2 and 2.8, but after 2.8, thymol blue has a yellow color. Once again, if I have a bromophenol blue, prior to the pH 3, the color of the indicator is yellow. After 4.6, it's a bluish purple, but the change happens between 3.0 and 4.6. In this range, it happens very fast. It's the steepest part. It happens very fast. It's a color change happens. So, and then they're asking you which indicator would you use for the following acid-base titration. So what you really have to do, they're giving you the steepest part of the titration curve. So the pH range about 4 to 10 and 7 to 10, 7 to 3. So you have to look at these indicators where see, do they change the color in that part? So this one is a solubility equilibrium. We will look at the solubility product expression KSP, and we will calculate KSP and predict that the precipitation will happen. So we will talk about the solubility of these ionic compounds, because those ionic compounds are salt. They are one of the products happening between acid and the base. And so we're forming salt. And once again, in chapter 4, we have the solubility rules. The certain salt of certain ions, they do not dissolve, they're insoluble. As you can see, it's in chapter 4. Some compounds are insoluble, but as a matter of fact, those compounds that in the chapter 4 we said insoluble, they are really actually very, very slightly soluble. So the KSP is, again, it's a constant. It's a solubility product constant, the same like equilibrium constant. And it allows us quantitatively predict how much of that insoluble compound will dissolve in the water. Yeah, they're insoluble, but there is slightly small amount, traces of that still can dissolve, and we can actually have a traces of ions in the water. So let's say I have AgCl. It's a solid, and you know when the chlorides, bromides, iodides from chapter 4, when they are they're soluble, except for when they have Ag plus, Pb2 plus and Hg22 plus ions. They combine, they become insoluble. So, but even though AgCl is insoluble, a very small very small amount of ions will be present in the water, Ag plus and Cl minus. So I can put together the KSP equilibrium constant. It's called solubility products. And again, it will be products, concentration of a products over the concentration of the reactant. But since the reactant is a solid, we do not put the solids or liquids in the expression of the equilibrium constant. So if the KSP is very small amount, so that means we do not have a lot of ions coming from that KSP, and we will say that that substance is has a very less solubility. So we can express the solubility of a substance using molar solubility, or the number of moles of solute in 1 liter of this saturated solution, mole per liter. Or we can express this just the solubility. It's the number of grams of solid in the 1 liter of the saturated solution, and both of those concentrations are at 25 degrees Celsius. So how to calculate the molar solubility from KSP? This procedure is exactly the same as the procedure for calculating pH of a weak acid or a weak base at equilibrium. So we have to construct the equilibrium table, the ice table, fill out what we know, figure out what we don't know. And let's say I have the silver bromide, the KSP of silver bromide. Take a look at the value, 10 to the negative 13. It is a very, very small amount. That means the ions Ag plus and Br minus are very small amount present there. So again, we will put together this the ice table, AgBr solid will make Ag plus and Br minus. So let's say at the beginning we have some amount of AgBr, but it's a solid. It doesn't matter. It's a solid. So at the beginning, the ions are not present. Their concentrations are 0. The reaction will proceed forward direction to make those ions plus S plus S. In this case, they're using, instead of X, this variable, they're using S. And at equilibrium, we have equilibrium concentration of those ions. So we will put this in expression of KSP, and we will find that the S equals to 8.8 times 7 molar. So that means the molar solubility, once again, what is a molar solubility, guys? Let's go back here. The number of moles of solute in 1 liter of a saturated solution. So, and here we can see that the molar solubility of AgBr is 8.8 times 10 to the negative 7 molar. So a very small solubility. But if we want to convert this to the solubility in gram per liter, so what we have to do, we have to say, okay, this is the molarity, that many mole in 1 liter. I will find the molar mass of AgBr in 1 mole. That many grams of AgBr is present. I will convert this to grams and divide by the liter. It will be 1.7 times 10 to the minus 4 grams of AgBr will be dissolved in 1 liter of solution. Once again, you have those calculations. Make sure you read the textbook, go over those problems, solve all those problems, so you will know how to work with them. So this is the solubility equilibrium. We can predict if we mix, let's say, two solutions, will the precipitate happen, if we will form a precipitate. So We will use here the Q, a reaction quotient, to predict when a precipitate will form. When the Q has the same form, Q has the same form of KSP. We know that reaction quotient. The only difference here is that the concentrations in the Q expressions, they are not equilibrium concentrations. They only will be equilibrium concentration if Q equals to the KSP. So let's say we're mixing solution containing Ag plus ion with another solution that contains Cl minus ion. So, okay, Q equals to the concentration of Ag plus initial times the concentration Cl minus initial. And if Q is less than KSP or even equals to the KSP, we will see no precipitate form. The precipitate only will be formed if the Q is greater than the KSP. So, and that's again, this is one of the sample. It says predict whether precipitate will form when each of the following is added to 650 ml of 0.008 molar potassium sulfate. So we are adding 250 ml of 0.004 molar barium chloride. So the barium sulfate can precipitate. But what we need to know, first of all, we need to know the KSP or barium sulfate. So this is what can, from the example A, what can precipitate. It's a barium sulfate, and the barium sulfate has the KSP. So now what we need to find the concentration of the sulfate. You see, we need to find the concentration of a sulfate. So what we're going to do, the concentration, let's go back over here. So we have 650 ml of the potassium sulfate, and we have 250 ml of 0.04 molar barium chloride. So let's first find the concentration of the barium ion. So the concentration of barium ion, don't forget when we're mixing those two solutions together, now the volume of the solution changes, 650 ml plus 250 ml. So barium, we have here 250 ml of 0.04 molar. So we will go back here and we'll say 250 ml multiply by this molarity. I'm gonna get mole, and then I will divide by the volume over here, and that will be the molarity. So the barium ion, we have 0.001 molar. For the SO4 2 minus ion, again, the total volume of the solution is the two volumes together, but I need to find the concentration of SO4 2 minus. And then once I have those, I will multiply those, and I will see that the Q equals to 6.4 times 10 to the negative 6. I will compare the Q with the KSP of barium sulfate. Q is greater than the KSP. Because Q is greater than the KSP, the precipitate of barium sulfate will occur. So once again, you have to understand when you are mixing, you can find from here the moles of the SO4. But the moles of SO4 from here, now to find the concentration, you have to divide into the volume. But the volume is now not just 650. You added 250 ml of this barium chloride. So now you're taking mole of this and dividing by the total volume. So that's very important. So make sure you will continue with that. So this is the um, another factor we have to talk about, how the solubility will be affected by the common ion effect. Common ion effect. So let's say we have a saturated solution of AgCl, and the expression of KSP, we know the expression of KSP. This is the KSP of AgCl equals to 1.6 times 10 to the negative 10. And we have Ag plus Cl minus. So in a solution in which AgCl is the only solute, here we know with the concentration of the Ag plus, it's the same as the concentration of Cl minus, and we can find that S equals to concentration of those equals to 1.3 times 10 to the negative 5. So let's say we are taking that AgCl now, and we are dissolving it not in the water, but we're dissolving AgCl in 0.1 molar solution of AgNO3. So now, do you see we have AgCl and AgNO3, they have a common ion. They have the same ion Ag plus from AgCl, and they have the same ion Ag plus in AgNO3. So in that case, the concentration of Ag plus and the Cl minus will not be equal to each other, because in this case, the Ag ion is actually coming from AgNO3. I have 0.1 molar Ag plus over there. So the concentration of Ag plus will be equal to 0.1 molar plus the concentration of Ag plus, which is coming from AgCl. So now let's put this into this expression of equilibrium. So the concentration of Ag plus will be 0.1 coming from that AgNO3 plus S, and the concentration of Cl minus is just the S. So since we're expecting S to be very small, that this expression 0.1 plus S, we will just simplify to 0.1 molar. We will put this into the expression. We will find S equals to 1.6 times 10 to the negative 9 molar. So now AgCl has a very small concentration of the ions now. That means it will be significantly less soluble in the AgNO3 than in the pure water, due to the fact that AgCl and AgNO3, they have the same ion, Ag plus. We call it the common ion effect. It's basically like you have, according to Le Chatelier principle, so you have the same Ag plus, the reaction actually will move to the left, and less of that will actually dissolve. So this is the same type of calculations that we perform right now, and I want you to go over that and address that. So once again, by the way, if I have, let's say, I am dissolving something in an acidic solution or in a basic solution, the hydronium ion concentration also can affect the solubility of the salts. So as you can see here, the solubility of substances can also depend on the pH of a solution. Insoluble bases, they tend to dissolve in acidic solution. So take a look at this one. I just look at this sentence. This is a base, magnesium hydroxide. It's an insoluble base. It will make magnesium ion, a small amount, of course, and the hydroxide ion. We can calculate the KSP of that, and we can find the at equilibrium with the pH equals to 10.45 because I have the OH minus. But in a solution with the pH of less than 10.45, the solubility of the magnesium hydroxide will increase. So let's say I have a magnesium hydroxide. Now I will, so this is what it will make, making magnesium ion and the hydroxide ion. So let's say I am, we added this solution, which is, let's say, adding the hydronium ions, and a strong acid, let's say. So as we can see, even if you will look at that, when you have H3O plus, I'm adding acid. But I'm adding acid to the solution of the magnesium hydroxide. That hydronium ion that I am adding, what it will do, it actually will react with this OH minus. Kind of will take out the OH minus out and will form the water. And because of that, because this OH minus is taking out, the reaction has to go forward, has to go to the right and make more of the OH minus. That means we will be having more ions present. So this is like overall reaction if I will add that. So this is, you can think about this once again as disturbing the equilibrium, and it's like a Le Chatelier principle. It's like a Le Chatelier principle. And so once again, you're adding acid. The added acid reacts with OH minus, makes water, and the reaction has to go to the right to make those ions back. The same thing you can talk about the solubility of salt that actually have basic ions.